log probability of this sequence of outcomes goes to the entropy of X. In fact, we're going to prove a number of things that leads us immediately to a data compression result. All right. So let's define the typical set. The epsilon typical set A epsilon super n with respect to the distribution P of X is defined by A epsilon super n equals the set of all sequences xn of symbols from the alphabet script X such that minus 1 over n log P of xn minus h is less than or equal to epsilon. And an example, if xi is our Bernoulli theta, then A epsilon super n is the set of all binary sequences in which the number of heads lies between p minus epsilon 1 less than p plus epsilon 2. All right, I'm not sure you can read that, but what I'm saying is that the overall definition is a sequence is typical if its probability is near 2 to the minus nh, that's what this means, is what you think it should be. But for a Bernoulli sequence that specializes to a sequence is epsilon typical. If the proportion of ones, I didn't divide by n here. 1 over n. Now you really can't read it. Okay. If the proportion of ones is close to p, and I said theta, so I better put theta here and theta here. Okay. Again, in words, a Bernoulli sequence is typical if the proportion of heads is what you think it should be, if it's epsilon close to theta. Okay, now we can prove a theorem. This is the AEP for independent, identically distributed sequences. If xi is IID. That is, this sequence of random variables is independent identically distributed. Then the following things are true. One is the probability that the random sequence x super n, if I wrote little x super n, that would be a possible outcome of the sequence. If I write capital X super n, that's the random variable, the random sequence itself. So it's the probability xn is typical, is greater than 1 minus epsilon for n sufficiently large. So in short, it deserves the word typical, because the probability x will be typical is close to 1. 2, if little xn, that is, if the sequence is typical, then that implies that P of probability, P of xn, equals 2 to the minus n h plus or minus epsilon. I might as well mention this loose notation right now. If I say this, what I really mean that P of xn is greater than or equal to this, where I put in what, plus epsilon, and less than or equal to this, where I put in minus epsilon. In short, if a sequence is typical, its probability is 2 to the minus n h plus or minus epsilon. And 3, the number of elements in n is less than or equal to 2 to the n h plus epsilon. Aha. All right, proof. Let's look at 2. That's definition. You see, if I just took exponentiated both sides, multiplied by n, I get precisely this statement. Okay? So that's the definition of typicality, so it's got to be true. 1 is the law of large numbers. Why? Because 1 over n summation log, 1 over n log of P of x super n, this random sequence. So this is the probability mass associated with a random sequence. Since this is random, so is log of the probability of it, which is a simple function of it. And so we look at this random variable. How has it behaved? Well, this is the product of P of xi, because they're independent identically distributed. And so this becomes 1 over n summation log of P of xi from I equals 1 to n. Now these are IID, random variables, or functions of the random variable xi, so it goes to the expected value, which is expected value of log p of x, which is equal to summation p of x log p of x, which is equal to minus the entropy. So in short, I've just applied the law of large numbers for products there. Now, this has some nice consequences, but let me first tell you how big the typical set is. It's not very big. So we have proof of 3. Let's prove it this way. 1 is equal to summation of p of x super n for all xn, x super n, and x super n. Yeah. The sum of the probabilities is 1. This is greater than or equal to the sum of these probabilities over little xn in a epsilon super. That's a subset of the set of all sequences of length n. But now, if xn is in a epsilon n, then p of xn is bounded by our definition here of what it means to be typical. That's number 2. P of xn is greater than 2 to the minus n h plus epsilon. So this is greater than or equal to summation of xn in a epsilon super n of 2 to the minus n h plus epsilon, because for all the typical sequences, the probability is by definition greater than that. Now this doesn't depend on x, so we bring it out and we get this is equal to 2 to the minus n h plus epsilon times the number of elements, a epsilon super n, in the typical set. That's the number of terms in the sum. And now we're done. 1 is greater than this, therefore a epsilon super n is less than 2 to the n h plus epsilon. Okay, that finishes proving the AEP. For independent random processes. Now, I'll give you the data compression thing right now, but before I do, I want to mention what the generalization of this is. The question is, does this generalize to, say, Markov processes? Well, Shannon stated this for IID and mentioned that it would be true for ergodic processes, but didn't give the proof. So Macmillan, around 56, proved that the AEP is true for Markov processes, where you define not the entropy, but the entropy rate, which we'll soon do. And so he generalized it to that. And then